In the chem activity number 7 and the corresponding video as well as live sessions, we will revisit the kinetic molecular theory. And the reason why I say revisit is because we saw some of its tenets in the early videos concerning gases where we explored the properties of different states of matter. We'll be looking at root mean square velocity or speed. As it turns out, I know physics professors are very concerned about distinguishing velocity from speed, but for some reason a chemist more or less thinks them to be about the same thing. And then finally in the live sessions we'll be looking at diffusion and effusion. So let's look at the kinetic molecular theory. So in some of the earlier videos, we were highlighting the idea of what an ideal gas is. And in part, an ideal gas is one that behaves according to the ideal gas law. But the reason why an ideal gas will behave according to the ideal gas law, in other words, PV is equal to nRT, is because the ideal gas will have certain properties. Now, to highlight this, I'm going to make a little bit of a sketch at the bottom here. So I'm going to make a box, and in this box, I'm going to have gas particles. And the idea is that I want to reflect a little bit more accurately if we could really see gas particles, how they would look relative to one another. And so I'm going to put a little dot there, and a little dot there, and a little dot there. And so this is meant to represent my gas particle. Now, of course, they're in constant motion, colliding with the walls of the container. So you got to picture that. But one of the other things I'm trying to emphasize is that they're very tiny compared to the container itself. And essentially, therefore, the volume of a gas is defined entirely by the size of the container. There's also a huge amount of space between each gas particle. So I realized in some of the simulations, it looked like the gas particles were all very crowded. But there's a huge space between gas particles, and that's why gas particles can be compressed. And because there's such a huge space between the gas particles essentially are not interacting in terms of any kinds of force of attraction or force of repulsion. So keep some of those things in mind. All right, so you can see we got these gas particles. They're very separated, lots of space between them. But of course, what's not shown is that they are, of course, moving, colliding with the walls of the container. So first of all, the volume of the individual particles can be essentially assumed to be negligible, so that the gas particle itself doesn't take up any space. And of course, if they're really quite separated, any volume that the gas particle would have is irrelevant, negligible. Next, the particles exert no forces on one another. That is, there are no forces of attraction. Now, if any of these two things, A and B, is not true, then the gas will not behave ideally. So under conditions, for example, of really low temperatures or really high pressures, you'll be bringing the gas particles closer together. They'll not be moving with the same sort of speed because their average kinetic energy is less. And also there's a chance of them exerting forces of attraction or forces of repulsion on one another. Under those conditions, the gas will not be behaving ideally. And in fact, under those conditions, you may be thinking the gas is now starting to look more like a liquid. So if you start to bring the particles closer together, they start to be attracted to one another or repelling one another. And the volume of the particle is starting to be significant relative to the size of the container. Then these gases are not going to be ideal. Next, the particles, of course, are in constant motion. And it's that constant motion and the subsequent collision between the particles and the walls of the container that causes the pressure of our gas. Ideal or not, that would cause the pressure. And then here is one of the key ideas that I'd like to highlight in this particular activity. The average kinetic energy of a collection of gas particles is assumed to be directly proportional to the temperature Kelvin. You double the temperature Kelvin, the average kinetic energy of that gas will double. The only way you can change the kinetic energy of a gas is to change its temperature. Any two gases at the same temperature would have the same average kinetic energy. So let's build on some of these ideas. Here you see what's called a Maxwell-Boltzmann energy distribution for a population of gas particles. Now, while that may seem kind of esoteric, one, a population of gas particles you can think of could be the air in the room in which you're currently seated, and in which case would be mainly nitrogen plus oxygen. There'd be a little bit of carbon dioxide and some other gases. So there's a population of gas particles. Now, Maxwell-Boltzmann refers to two scientists who did a lot of work on, in a sense, statistical analysis of populations of particles, gas particles. They did this work in the later 1800s, and they derived a lot of important ideas. So those are two individuals represented by that Maxwell-Boltzmann name. So let us say that we're looking at the air particles in the room in which you're seated. And we look at, well, what sort of energy distribution do they have? And so just to highlight, let's say that this distribution here is showing us, for a temperature of 298 Kelvin, what the distribution of energy would be for our nitrogen plus oxygen particles, which of course essentially constitute most of the molecules in air. Now, often students at first have trouble reading this graph. Note that in the x-axis, we're looking at increasing energy. Right, so I'm rewriting what's already on the x-axis, but just to highlight, we're looking at energy here, and it's the idea that particles that are found in this portion of the graph have very, very high energy. But at a particular temperature, there's also a group of particles that have very low energy. So there's this full distribution. The EMP stands for the energy most probable. And that is now pointing to how we read the y-axis. So the y-axis sometimes is stated as probability, or it could be fraction of particles, or it could be actually the number of particles. So going upwards in the y-axis, we have more particles, or more chance that particles would have a certain energy. So this is why we say the most probable energy. And so you can see most of the particles will have this level of energy. So we have some particles with very little energy. We have some particles with really high energy. Most of the particles have this amount of energy. Now there's also the average energy. And so this would correspond to, for instance, our concept of the average kinetic energy. So this term here, in a sense, represents our average kinetic energy. So you can see that most of the particles don't in fact have the average kinetic energy. And the reason why the average is skewed towards the right here is it's taking into account that there are particles that have really, really high energies. And in fact, we argue that this graph at this position right here, it never actually intersects or comes to the x-axis. We don't know what the highest energy of a particle can be at any particular temperature. Now, the chance or the number of particles that would have really high energy at, let's say, really low temperatures would be quite small. But still, there would be the odd particle that would have quite a high energy. So let us say now that we change the temperature of our air, and let's say we increase it by 100 degrees. Now this is going to be somewhat of a qualitative analysis, so my graph isn't going to look very exact, but it'll give you a general sense of how this graph is going to change. So I'm just going to change my pen color, so this is going to look different. That is, my next line is going to look different. And let us take a temperature now at, let's say, 398 Kelvin. So we're going to bump up the temperature by 100 degrees. It's still going to be the same population of gas particles. So in other words, we're talking about the gases and air. And one of the things I want to emphasize is the area under this graph has to stay constant. So the area under this graph represents the total number of particles. And as you might imagine, based on the statement right here, as the temperature in Kelvin increases, the average kinetic energy should also increase. And so what's going to happen is that this graph is going to spread out so that we have more particles that have more energy, but there's still going to be some particles that have practically no energy. So your graph is going to look something like the following. Now again, this is not very quantitative, but it gives you a rough sense of how this is going to look. So we would say at this higher temperature, right about at this spot right here, and then moving down to the x-axis, this would be the energy most probable at that higher temperature. And I would guesstimate, for instance, that about right here, I would have the average kinetic energy. So hopefully it's clear to you that the average kinetic energy has indeed increased at that higher temperature. But now we've got particles that have very much higher energies. We have particles that still have low energy. So you can see that this curve, in a sense, has flattened down. There are less particles that have the most probable energy. Perhaps you can extrapolate that if we were to increase the temperature to, let's say, 2000 Kelvin, yes, we'd have a lot of particles, or many more particles that would have really high energies, but this curve would flatten out substantially. So actually, let's just see if we can give a go of this. I'm going to use my green pen. And now let's say we talk about air at 2000 Kelvin. All right, so this is still our nitrogen and oxygen. And perhaps the graph might look something like the following. And so the idea is that it really spreads out the different energies that the particles have. Now, I haven't been so careful in making sure that the axes match, but hopefully you get the idea that this really spreads out. So fewer and fewer particles would have any particular energy, but the energies available would be very much more spread out. And certainly the average kinetic energy would be quite a bit higher than that at 398 and 298. So here we're showing how the change in temperature affects the average kinetic energy and the distribution of energies for particles.